Hi, good evening. So I think you had joined last week as well, right? So welcome back again. So your name is, I think, Aruna or Aryan. I don't exactly recall. Anurag. Oh, sorry. Yeah, yeah, sure. Welcome, Anurag. So I was just waiting for more people to join, but I think yeah, we can get started. So are you able to see my screen? Okay. Yeah, sure. Thanks. Yeah. So I'll be just briefly going through the content for the second week, and then we can move on to any problems. So, so before we start, I just wanted to ask whether you have any questions from your side regarding the content for this week or previous week, anything, any questions from your side? Okay, yeah, sure. So I think we can start. So, so yeah, so this, so we are in week two, and the main theme of this week is free vibrations of single degree of freedom systems. Uh, and these are the topics that have been covered in this week. So the first is basically undamped free vibrations. Then the energy method has been covered. Then the damped free vibrations have been covered. And basically, there are different types of damping observed, which are discussed, like viscous damping, Coulomb damping, and other kinds of damping. And the concept of logarithmic decrement in systems has been described. So maybe we can just go through the uh, content of this week. So in undamped free vibration, we can derive the equation of motion using Newton's second law. And let us say we have a system, single spring mass system, uh, where we get the final equation of motion in this form. So mx double dot plus kx equal to 0. Now to find the solution to this equation of motion, we assume a certain form of a solution. So here it is assumed as x of t as a function of time is c e to the power st. And then we substitute this solution into the differential equation, and we get the equation of this form. ms square plus k equal to 0. So this will have this like solution where c is equal to 0, which would mean that the displacement itself x of t is identically 0. So we don't want a situation like that. So we choose ms square plus k equal to 0. So we get two roots. So s is plus or minus root of minus k by m, or plus or minus I omega n. So where omega n is the natural frequency, which is root of k by m. So k is the stiffness and m is the mass. And so now we can write down the general solution in this form, or alternatively we can also write it as a sum of sine and cosine functions. So these complex numbers can be written as a sum of basically, so e raised to I omega n t can be written as cos omega n t plus I sine omega n t. So using that concept, we can also write it down as in this form, the general solution. And the unknown constants C1 and C2, or A1 and A2, whatever we consider, so they can be found out using the initial conditions. So the displacement at time t equal to 0 and the velocity at time t equal to 0. So they can be used to find out the values of the constants A1 and A2, and we get the final solution in this form. So then we can also write down the solution in this form, where x of t is a cos omega n t minus phi. So we can write it in terms of amplitude and phase. So those two amplitudes A1 and A2, they can be combined together to get the uh, resultant amplitude A. So this is the equation for that, and the phase difference can be written using this equation. So we can also alternatively assume the solution in this form, which is x of t is a naught sine omega n t plus phi. So instead of cos, we can write it as a sine function. So similarly, we can also get expressions for the amplitude and phase values. Uh, so then we can plot the resultant uh, displacement variation with respect to time for undamped free vibrations. So as we have studied earlier, simple harmonic motion can be expressed as a projection of circular motion either on the x or y axis. So similarly, we can apply this concept over here as well. So let us say that we have a phasor uh, a vector which is rotating at a angular velocity omega n. So we can draw another phasor which is an angle phi apart. So then we can write the resultant angle that is made with the x-axis as omega nt minus phi. So the if we follow this phasor which is at angle omega nt minus phi, we will get this and project this motion onto the x-axis. So then we will get a curve of this form. So, so the meaning of the has been physically shown of the basically the amplitude, and so this amplitude is basically the amplitude that so the amplitude that we calculate from the initial conditions. So this is shown like that, and the time period uh, is also shown over here in this figure. Now, if we move on to damped free vibration, so similarly, we can write down the general differential equation of motion, and we follow a similar approach of substituting the solution of this form of an exponential function. And then we get the general characteristic equation in terms of S, and we solve this as a quadratic equation to get the roots for S. So we get the two roots for S, which in terms of the mass, stiffness, and the damping coefficient. So we can write down the general solution in this similar form. So now the nature of these roots will depend on the values of the mass, stiffness, and damping ratio. So we can either have two real roots or two imaginary roots, and so on. So the first case is when, let us say, we when uh, the expression under the root is if it is negative, so then we get this condition. So before that, we basically define a quantity called damping ratio. So which is basically the ratio of the damping present in the system to the critical damping. So we can write down the solution. So if the first case would be if we have two real roots. So the if those are two distinct real roots, so then the system is called as uh, overdamped. And if the system is underdamped, or if that is like zeta is less than 1, so then we get two complex roots. So so these are the general forms of solution. So let us say if we take the first case of underdamped system, so then we get the two roots S1 and S2 like that in this form. And this is the overall displacement expression. So we can like write it as a sum of sine and cosine functions, and the amplitudes of the sine and cosine functions can be calculated from the initial conditions. So this is like a general plot of the motion when damping is present in the system. So this is the case, the plot for the underdamped system. So where the amplitude will go on decaying with respect to time. So the maxima of each in each time period. So if we join them together, we will basically get an envelope. So the maxima and minima of the curve. So we can, if we can, like, join them, so that will form an envelope, which is x e to the power minus zeta omega nt. So this curve actually moves between this envelope. So we can calculate the time period of the damped vibrations. So that is basically 2 pi upon omega d. So omega d is the damped uh, angular frequency. Now the second case is critically damped system, where zeta is equal to 1, or basically the damping present in the system is same as the critical damping. So then in that case, we have two equal real roots. So in that case, we get the resultant displacement in this form. So C1 plus C2t into the power into e to the power minus omega nt. So this is the nature of the resultant displacement in case of critically damped systems. So again, we get two unknown constants C1 and C2, which we can calculate from the initial conditions. So in this case, we do not see any oscillations. So the displacement will go to a maximum value and then go on decaying. So in case we have sorry, two distinct real roots, then that system is called as overdamped system. So if the damping ratio is greater than 1, so then we will have two distinct real roots. So we call them as S1 and S2, and then we can write down the general solution in this form. So generally in practical applications like vehicle suspensions or so, we would generally prefer underdamped systems so as to uh, minimize energy loss, too much of energy loss with damping. So these are the typical nature of the plot.
Explanation, sir. So the
Yes,
value of S1 and S2 for case 3 overdamped
yes,
is. So what is the difference between overdamped and underdamped S1 and S2 values?
yes. So in case of underdamped systems, basically we get the that zeta is if it is less than 1. So then uh, this part c square minus 4km, this will be actually negative. So root of a negative number, so that will be uh, we call it as I into root of 4mk minus c square. So that if we write down s1 and s1 and s2 as like root of zeta square minus 1, and if zeta is less than 1, so then root of a negative number, it will be a imaginary number. So then S1 and S2 are actually complex numbers in an underdamped system. Whereas when zeta is greater than 1, then we will get two distinct real roots. So root of zeta square minus 1, so it will be a positive real number, right? So because zeta square is greater than 1, so then the quantity which is under the root, it will be positive. So we will get two distinct real roots, whereas in underdamped system we will get two complex roots. So does that answer your question?
Yes, sir.
Okay. Yeah, sure. So then, this is the general nature of the plots for the three different types of motion that we just discussed. So, like critically damped systems, we would generally, prefer if where we want to, we do not want any oscillations to occur. So, for example, there are like there are some dampers used in doors which are actually which close automatically. So you might have seen like in some cases like in offices or places like there we if we want to open a door and release it, it has a mechanism to close the door automatically. So if you would have observed that there would be a piston cylinder on top somewhere on the door above over our head. So you would have observed that there is some piston cylinder kind of thing. So that is the damper that is used. So when we open the door and release it, it will slowly close and then finally it will stop. So there, if we design it like a underdamped system, then you might see that the system will kind of it will close, but it will kind of show some oscillations. But we don't want to have any oscillations in that case. So there we can design it as a critically damped or over damped system. So it will slowly, the amplitude will increase and then decay slowly. So you can relate that with the door example because you would have seen it in everyday life, I think. Whereas,
Sir, what material?
sorry.
So, so what is used in that piston and cylinder? Which material actually?
Yeah, so it can be some kind of oil, and which is filled inside that piston, and sorry, in the inside the cylinder, and the piston, it has a disc which is called like orifice. So you would have heard the term orifice. So it is basically a disc which has some holes in it. So when the piston pushes against the oil, then the oil is forced to pass through that holes, and then that creates some resistance to the motion of the piston, so which basically creates some kind of friction between the fluid and the piston. So that is because of the viscous drag or viscous forces which are exerted by the oil, so between the oil and the piston. So that creates the viscous damping. So maybe I can try to show you some video on YouTube. So yeah, maybe I'll look for some video or something where which I think you can it can help you understand better. So maybe next time I'll try to share that video with you. So but basically that's what it is, that it contains oil, which so the piston will push the oil, and the friction between the oil and the orifice disc, that will create the damping effect. So does that answer the question?
Yes, sir.
Yeah, sure. So then we have the concept of logarithmic decrement. So which is generally more important in case of the underdamped oscillations. So so as we see that uh, the amplitude keeps on fluctuating, but the overall amplitude is showing a decaying trend. So let us say if we note like the amplitudes at certain point of time, and then if we want to find out what is the damping present in the system uh, by observing the amplitude. So then the method of logarithmic decrement, we can use it to calculate what is the damping present in the system by the ratio of successive amplitudes. So let us say if we mark the amplitude x1 at time t1, so somewhere on this curve, and then the corresponding point in the next cycle after one time period, so that is basically after one complete cycle, so then that amplitude is, let us say, x2, which is at time t2. So the difference between time t1 and t2 is this time period. So if we record this value, so and if we find take the ratio of x1 and x2, so from that we can calculate the damping ratio. um, so the logarithmic decrement is the quantity which is log of x1 by x2. So we can calculate that, and it is basically zeta, omega, and tau of d. So it can be derived, and if we express the uh, quantity tau of d, or basically the time period, in terms of the damped natural frequency, so then we can express this whole quantity in terms of the damping ratio zeta. Uh,
Sir, how
yes.
is this X1 and X2 determined by time interval, or is it a fixed point?
No, so if we suppose record the the amplitude of vibrations through some sensor, and we try to plot it. So if we can take this location x1, this amplitude x1 at any time in the cycle. So it can be at any point in certain cycle, and then we note the corresponding point x2 after one complete cycle starting from x1. So x1 can be anywhere. So it can be, right now it is marked over here, this x1, but it can actually be anywhere on this curve. So it can be even on the negative side. But the only thing is that we are looking at the amplitudes which are successively one cycle or two cycles or three cycles apart.
Okay, sir. Thank you, sir.
Yeah. So then like how we know the equation of like the we have found out like how we can find the solution of uh, for the undamped underdamped case. uh, like we know the nature of the solution, so we can just substitute the time t1. So we already know this curve uh, based on our initial conditions. So we can calculate x1 at point time t equal to t1 and x2 at time t equal to t2. So if we are calculating theoretically, so then uh, this ratio actually works out to be zeta omega n into tau t, which is time period. So it can be expressed in terms of the damping ratio zeta only. And if zeta is considered to be very small, then this logarithmic decrement is only approximately equal to 2 pi into zeta. So basically using this logarithmic decrement, we can calculate the damping ratio. So this was about the content of for this week. So I'll be sharing the slides. So no need to memorize or anything like this content. So you can always derive these things from the basic equations. So no need to be afraid of these big equations or anything. You don't need to actually memorize. You just need to understand, like you start with some certain differential equation. Uh, and then you assume a certain form of a solution, and then calculate the uh, like basically the you determine the roots of the characteristic equation, or and then predict the nature of the roots based on the physical quantities like mass, stiffness, and damping ratio. And then based on that, we can derive the solutions. And from the initial conditions, we can get the unknown constants uh, of the which are present in the solution. So that is a general approach for any vibration problem. And this logarithmic decrement is like a quantity which is derived from the basic nature of the solutions itself. So that is a technique which is helpful in terms of, like, if we are doing some experiments and then we want to find out the value of damping, then this is a concept that we can use. So that was about the content for this week. So any questions?
No, sir.
Okay, sure. So if you are actually interested in doing some experiments yourself, uh, on, like, if you want to actually do vibration experiments, uh, then you can actually use your own smartphone as well to do some vibration experiments. So if you are interested, I can actually talk about that. So are you interested?
Yes, sir.
Yeah, so you can do like this kind of activity. So our smartphones have like lots of sensors like accelerometers, temperature sensors, color sensors, humidity, proximity, gyro sensors, magnetometer. So all, so for example, the screen auto rotate feature that comes, how does the mobile know that the phone has, like, rotated? So it knows it from that the gyro sensor, so which senses the rotation. So if we rotate our phone, so then the gyro sensor will uh, you know recognize that our phone has rotated, and based on that it will rotate the display. So similarly, accelerometer is a sensor which gives us the output proportional to our acceleration. Magnetometer sensors are basically similar to a compass. In olden days, you would have probably studied somewhere that people used to use compass to show the, to indicate the north south direction. So at any location which is the north and south direction, so to find out our basically our direction, so it is used for navigational purposes. So in Google Maps, in navigations, so in which direction we are facing, and from that Google Maps will determine the route based on our magnetometer sensor. So things like that. So these are the different uses of the sensors. So we can use the outputs of these sensors in some kind of vibration experiments. So generally the smartphones have X, Y, Z axis, like the way it is shown in this figure. So the orientation is generally like that. And there are some apps which can access the data from these sensors and record it. So that in Android as well as iOS devices, we have this app known as Firefox, or there is another app called Physics Toolbox. So you can install any of these apps and use it to record data from these sensors. So for example, you can do like a simple experiment, like a simple pendulum. So you can use a simple ruler, metallic ruler, and stick your phone to that ruler using some tape or something like that, and then use your phone itself as the pendulum bob, and switch on this app, and start recording the data, and give the ruler some kind of initial displacement, and let the ruler go, and then you will see that the phone will oscillate, and the phone acts as a simple like pendulum, pendulum bob, and at the same time it is also recording sensor data. So it can save the sensor data using some Excel, in the form of an Excel file or something like that. And then once you record that data, you can export it as an Excel file or CSV file, and then use it to estimate things like natural frequency or logarithmic decrement. So things like that. So this is one interesting application of, we have I think most of the people nowadays have smartphones, so you can actually use them for vibration experiments. So I think you can try that, and let me know if you have any questions. So so now I think we can move on to the problem solving part. So uh, picked up some uh, I have picked up some sample problems from like some sources, and put them together, and wanted to demonstrate how to solve those problems. So shall we start with that?
Yes, sir.
Sure. Yeah, so I'll just give me a moment. I'll just set up my Jamboard. So are you able to see my screen?
Yes, sir.
Okay, sure. So let's get started with the problems now. So I think you would have studied the uh, concept of degrees of freedom. So we have this.
Yes, sir.
Yes. Yeah, you were saying something?
No, sir. I have studied this in.
Yeah, sure. So So you would have studied this concept of degrees of freedom. So let us say if we have been given some system like this, uh, where there are two masses, like one pendulum bob like M1, and then to that bob M1 we have another pendulum bob M2. So now if you want to find out how many degrees of freedom does this system have, so so how will we find out that? So any idea?
So first we will find the independent degree of freedom of each of the bobs. So one and one. So I think two.
Okay. So do you know what is the definition of like the degrees of freedom? So
So it defines the. It is the number which represents the moment of any object and how many direction it can move.
okay, right. So basically, if you want to describe it in more of a mathematical kind of way, so we can say that it is the number of uh, coordinates that are required to uniquely describe its the position of any system or component. So let us say if we take the mass m1, so in order to uniquely define where it is, so if we define some coordinate system x, y, z, so so then we know that it is already in xy plane, so the z coordinate is always fixed. Then it is suspended from this fixed point at this, let us say this rod L1 is rigid and does not change its length. So then it is uh, constrained to move in a certain fashion in the xy plane. So the only independent variable which can be used, it can be either theta 1, or we can use the position like the coordinate y1 or x1. So if we choose x1 and y1, they are actually related through theta 1. So how are they are related? It's basically y1 by x1 is uh, or rather x1 by y1, I should say, is tan of theta 1. So we have either x1 or y1 or theta 1. One of them is can be a unique coordinate for this mass m1, and alternatively we can also like for the second mass, now to uniquely describe its position, so it will be dependent on where this mass m1 is located, and in addition to that it will also depend on uh, theta 2. So if we know theta 1 and theta 2, because the length L2 is known and it is fixed, so we can write down x2 in terms of x1. So x2 is equal to x1 plus L2 sine theta 2, right? So then, so now we know x2 and L2 is also known. So we can also find out what is the value of y2. So which is like the location, the coordinate up to this point m2. So then y2 can also be written in terms of y1. So it is y1 plus L2 cos theta 2. So we can use the independent coordinates either x1 and x2, or we can use y1, y2, or theta 1, theta 2, any combinations of these, but we can basically use only two of them and find out where both these masses are located, and so that is why the degree of freedom is basically 2. So two coordinates are sufficient in this example. So you are right, degrees of freedom are 2. So any questions?
No, sir.
Okay. So yeah, in this question, so we know that the free vibrations we can the equation of motion is 4x double dot plus 64x equal to 0. Now if you want to find out the uh, natural frequency of this motion, so then how do we find out how will we calculate the natural frequency from this differential equation? So the general form of the differential equation is x double dot plus omega n square x is equal to 0. So we can compare the coefficients between them. So we can reduce this equation to x double dot plus 64 by 4 x equal to 0. So 64 by 4 is 16. So basically omega n square is equal to 16. So which means that omega n is equal to 4 radians per second. So like that we can find out different quantities uh, from the differential equation. So this is an undamped this differential equation represents undamped vibrations. So the natural frequency is the only important characteristic in this case. So if you have any question, please do stop me at any point of time.
Okay,
So
sir.
yeah. So we have the next question where it is given that some a mass is attached to the end of a spring where stiffness is given and the damping provided is 20% the critical value. So then the frequency of damped vibrations is what? So if we write down the general equation of motion, so it can be written in the form of Cx dot plus Kx is equal to 0. And so so if we want to find out the undamped natural frequency, so that will be basically root of k by m, right? So so the damped natural frequency is basically omega n into root of 1 minus zeta square for the damped vibrations. So it is given that the damping provided is 20% of the critical value. So basically C upon CC, it is critical damping. So that is basically 20% or 0.2. So basically zeta is equal to 0.2. So we know omega n. So omega n, it is basically square root of 800 by 2. So 2 kg and stiffness of 800 Newton per meter. So which is square root of 400, which is 20 radians per second. And the omega d, we can calculate it as 20 into root of 1 minus 0.2 square. So it will be It should be something around 19.6, I guess. Should be something around 19.6 radians per second, approximately. So that is how we can calculate. Uh, so if we have been given the mass, stiffness, and the damping present in the system, we can find out the damped natural frequency. So, however, if we are doing some experiments and if we do not know or we generally don't know the damping present in the system, so we can calculate the uh, amount of damping present in the system based on the logarithmic decrement. So the next problem is this one, where so let us we have a mass which is suspended between two springs K1 and K2. So the values of K1 and K2 have been given, and this mass, the weight is 10 kg. So we need to find out the natural frequency of this system. So now, how do we proceed with this problem? So any idea?
Sorry, sir.
No idea. Any idea?
No, sir.
No. Okay. So yeah, so you can think in terms of like, uh, so when we have to find out the natural frequency, the the natural frequency is given by root of k by m. So generally, if we can, so this system has two springs and one mass. So if we are able to reduce it in terms of a single mass and single spring, so then so the equivalent K value or stiffness value divided by the equivalent whatever total mass net mass present in the system, so that will be the natural frequency. So our job is to find out the equivalent stiffness present in this system. So now to find out uh, the equivalent stiffness, we need to first find out whether these springs are in series or parallel, whatever. So what do you think? So these springs are in series or parallel?
So series.
Okay. Why do you think that they are in series?
They will add up, I think so. Sorry, sir. Sir, they are in parallel. You explained the last time.
Yeah. So they are actually in parallel. Why they are in parallel? Because uh, their deflection is same. Uh, so they are actually mounted between the same, let us say, fixed support. So now if we move this thing by x, so this spring will get stretched by x and this spring will compress by the same amount x. So let us say the forces F1 and F2, and there will be some weight mg also acting, let us say. So the deflection, let us say delta 1 and delta 2 of these springs, they will be related in such a way that delta 1 is equal to delta 2, whereas the total spring force acting on this system is basically uh, so now let us say that, so we have assumed that, let us say if we push this mass down by x, then this force F1 will be tensile and this other spring will exert some compressive force F2. So the total force equivalent force is basically F1 plus F2, which is, so we can write down the force F1 as K1 delta 1 and F2 as K2 delta 2. So now we have already said that delta 1 is equal to delta 2. So it is basically K1 plus K2 into delta 1 or delta 2, whichever. So which we can write it in terms of K equivalent into delta 1 or delta 2, whatever. So which means that K equivalent is K1 plus K2. So which is basically root of K1 plus K2 by M. So it is basically, so 20.25 plus 29.75. So which adds up to 50. So it is Newton per mm. So be careful about the units. So which is basically same as writing it as 50,000 by mass. So which is 10,000, which is 10 kg. So it is basically root of 5,000. So it will be something around 70.7 radians per second. So that's the natural frequency of this system. So any doubt in this question?
Sir, how this conversion I didn't understand. So Newton to
Newton per mm.
kg.
Yeah. So Newton per mm will be basically, so generally we have with the unit is Newton per meter. Oh yeah. So it's actually Newton per meter. So if we write it in terms of Newton per mm, so it basically means that it is Newton per meter into, sorry. So it is basically Newton per meter, like into 1 upon 10 to the power minus 3. So 1 upon 10 to the power minus 3. Why? Because we are like using the millimeter. So then we can say it is basically 1 Newton per mm is same as 1000 Newton per meter. So
Sir, but the weight, the mass is in kg.
mass is in kg, right? So it is already 10 and the stiffness value is in Newton per mm. So it is 50 Newton per mm. So 50 newtons per mm. So it is basically 50 into 1000 Newton per meter.
Sir, doesn't we multiply with gravity to convert into Newton, the mass?
No, it's not about mass. It's actually the unit of stiffness, Newton per meter. And uh, we are not actually converting weight. This is not like about weight. So the mass is 10 kg. So that is already given. And we write the stiffness in terms of Newton per meter. So the ratio of K by M, square root of that will basically give us the angular frequency in radians per second.
Okay, sir.
Is that okay?
Yes, sir.
So So the next question is where we have been given the equation of motion for the damped viscous vibration. So it is 5x double dot plus 6x dot plus 5x is equal to 0. So we can alternatively also write it as x double dot plus 6 by 5 x dot plus x is equal to 0. So if we write the general form of the differential equation, it can be written as so x double dot plus 2 zeta omega n x dot plus omega n square x is equal to 0. So then if we compare the coefficients, so we get that omega n square is actually 1 or omega n is 1 and 2 zeta omega n will be 6 by 5. So which gives that 2 zeta is equal to 6 by 5 or which gives zeta is equal to 6 by 10 which is 0.6. So the correct option is zeta is equal to 0.6. So is that okay? Any doubts?
Yes, sir. No, sir. No doubt.
Yeah. Okay. Yeah. So if this question is like about logarithmic decrement. So we just saw some time back that we can write down the logarithmic decrement in terms of the damping present in the system. So it is asked in this question if in any spring mass system if the mass if we reduce it to half and the spring stiffness is doubled, then what will happen to the logarithmic decrement? So can you tell me?
Sir, unchanged.
Yes, it is unchanged because the logarithmic decrement we can write it in terms of damping ratio only. So which is actually independent of the uh, mass. So it is mass or stiffness will not affect this thing. So it will only depend on the damping ratio. So it will be unchanged, right? Yeah. So then we have this problem. So this question was asked in this year's GATE examination. So we will look at some examples which are from previous year's GATE question paper for mechanical engineering. So in this question we have a simple spring mass system. So it shows that this mass it is attached to two different springs and the spring constant is given, and it is also given that the horizontal surface is frictionless, and it has been asked that what is the time taken by the block to complete 10 oscillations. So for that, so how do you think we can solve this problem? Any idea how to solve this problem?
So first we find the damped frequency, then with that finding the time period. I think so.
Yeah, so here actually there is no damping in this case. So there is only a simple spring mass system. So you are right, we can find out the time period and the time required to take complete 10 oscillations. It's actually 10 times the time period itself. So what will be the natural frequency in this case? So if we want to write down it in the form of an expression. So what will be the uh, expression? So omega n is what?
So root over k upon m.
Yeah, so here there are two springs, right, in parallel. So now they will add up, right?
Yes, sir.
So it will be
K1.
actually 2k by m, right?
Yes, sir.
So it's basically 2 into 1000 by 20. So root of 100, which is 10 radians per second. So what is the time period in terms of the omega n?
2 pi upon omega n.
Right. So it is 2 pi upon omega n. So which is 2 pi upon 10. So we have been asked to calculate the value of 10 times this time period. So 10 times 2 pi upon 10. So which is just 2 pi. So 2 into 3.14, which is 6.28 seconds. Right?
Yes, sir.
So yeah, so let's move on to another question. So this question is from GATE paper 2021 for mechanical engineering. So let me ask. So are you so Anurag? So do you plan to appear for GATE exam or anything in future, if at
Yes,
all?
sir. I am currently third year. I will give this year.
Okay, okay, sure. So are you preparing?
Yes, sir. Trying little.
Okay, sure. So I think you can actually start preparing. So I actually have picked up these questions from the GATE previous year's GATE question papers itself. So I think this can help you in that way.
Sure, sir.
Yeah. So this question it's about this question actually involves some damping. Uh, so here we have been given that there is a dash pot So it is like same as a piston cylinder. So you call it like dashpot or piston cylinder or damper or what. It actually means the same thing. So so it is given that the amplitude of the free vibrations reduces from 8 mm to 1.5 mm in 3 cycles now. So then we have to find out what is the damping ratio. So so which concept do you think we should apply here to find out the damping ratio now?
Sorry, sir. No idea.
No idea? Okay. So it is basically damped free vibrations. Uh, so we just discussed about this concept of logarithmic decrement, right? So let's assume that this system is under damped. So then the amplitude or displacement will basically vary like this somewhere somewhat. So then we just looked at that we will mark, let us say, some point like x1 with displacement x1 at some time t1. So then after one cycle it will be x2 at time t2. So then another point can be x3 after two cycles. So that can be called as at time t3. And then we can also mark another point x4, which is after three cycles. So after one cycle, the displacement is x2. After two cycles, it is x3, and after three cycles, it is x4. So we have been given that x1 is basically was 8 somewhere, and x4 is 1.5. So it's basically three cycles. So the time difference between T4 minus T1, so that is three time periods. So then we can apply the concept of logarithmic decrement. So how we will apply that? So so let us say we so instead of directly applying the formula for logarithmic decrement, so let's actually just look at how we actually get that thing. So we can write out the general form of the solution as, so we know what is omega n. We basically omega n is root k by m, and omega d is omega n into root of 1 minus zeta square. So we know we have to find out zeta itself. So we have marked the point x1 at point t1. So the value of x1 will be a e raised to minus zeta omega n t1 into cos omega d t1 plus phi, and the value x4 is a e raised to minus zeta omega n t4 cos omega d t4 plus phi. So now we know that t4 is t1 plus 3 time periods after 3 cycles, right? So it is basically T1 plus 3 into 2 pi upon omega d, right? So then,
Yes, sir.
yeah, so then we can write it as e raised to minus zeta omega n T1 plus 6 pi upon omega d into cos of omega d into T1 plus 6 pi upon omega d plus phi. So now we know the property of trigonometric functions, so that cos of t is same as cos of t plus time period, right? So the value of the cos, cosine or sine function after one time period, or let us say n time periods, it will be same as the value of the cosine function at that point. So basically what I mean to say is that, so if I mark this point, so where it will it be after one cycle, it will be here. So again after one cycle, one more cycle, it will be here. So this value will keep on, will remain same after every complete cycle. So here we can apply that same concept. So then we get that x4 is basically a e to the power minus zeta omega n t1 into e to the power minus zeta omega n into 6 pi upon omega d into, so we can use this concept and like write it as cos of omega t t1 plus phi plus 6 pi. So which is same, so this value of this cosine thing, it is same as value of only this thing, right?
Yes, sir.
So then basically, so basically x4 is, into 6 pi upon omega d. So we can write omega d again in terms of zeta and omega n, so which is omega n root of 1 minus zeta square into cos of omega d t1 plus phi, whereas x1 is a e to the power minus zeta omega n t1 cos of omega d t1 plus phi. So now when we take the ratio of x1 by x4, we will get, so this term a e to the power minus zeta omega n t1, that is uh, still, it is common between both of them. So that will get cancelled when we divide, take the ratio. And this term cos omega d t1 plus 5 will also get cancelled. So we will be just left with e to the power, and this term omega n and omega n will also get cancelled. So we will get basically minus 6 pi zeta upon root of 1 minus zeta square. Or if we take the natural log of both sides, or so we will get ln of x1 by x4, that is, so log of e to the power something is this, the exponent only. So we can write it as 6 pi zeta upon root of 1 minus zeta square. So now here we have been given that x1 is 8 and x4 is 1.5. So basically log of 8 by 1.5 is 6 pi zeta upon root of 1 minus zeta square. So we will get, so let us call this value as some uh, value, let us say it is beta, some beta. So we will get a quadratic equation in terms of zeta, so which is 6 pi zeta upon root of 1 minus zeta square is beta, and if we square both the sides, so we will get basically, so squaring both sides, we will get, so beta square into 1 minus zeta square is equal to 36 pi square zeta square. So therefore we will get beta square is equal to 36 pi square plus beta square into zeta square. So we will get zeta in terms of beta. So we know the value of beta, we can calculate that and just substitute it in terms of in this equation. So we will get the value of zeta, which is the damping ratio. So this is how we actually can use the concept of logarithmic decrement to calculate the damping ratio. So any questions?
No, sir.
Okay. So I think you can calculate this value of beta and then substitute it to get the damping ratio. I think that can be done. So let me move on to another problem. So in this problem, this is from GATE 2021 question paper. So it is given that uh, so there is a mass m, small m, which is suspended from a rope through a pulley. So that pulley has a moment of inertia j and a radius small r, and so it is attached to a, it is basically fixed to a wall used through a spring k, and it is given that there is no slipping between the pulley and the rope. Yes, you had some question. Yes.
Sir, can you tell the answer of the previous one?
numerical answer. Uh,
Yes.
I actually have not calculated it yet. So let me check. So, so the value of beta, it is coming out to be around 1.67, and the value of damping ratio, I am just calculating that. It is, so I am getting the answer as 0.088, something like that.
Yes, sir.
Yeah. Yeah. So let's move to the next question. So we have this system. So we have to find out the uh, natural frequency of this system. So any idea how we can go, how to solve this problem?
First we calculate the tension force, I think, due to
Okay.
the weight.
Okay.
Then we will equate it, and then we will find the frequency.
Equate what?
So the tension force on the string.
Tension force on the string. You will equate it to what?
Um, Sorry, sir. No, no, sir.
Okay. So yeah. So the key thing in this question is basically to uh, find out the relation between. Sorry, I again lost the screen. Just a moment.
Yes.
Yeah. So the key thing in this question is to basically find out the relation between the movement of mass m. So it, let us say we assume that this mass small m will just move vertically up and down. It will not go here and there anywhere. It will just go vertically up and down, and this disk will rotate this way theta, by some angle theta here, like either clockwise anti-clockwise depending on where the mass is. So now how do we find out if what is the relation between this motion, up and down motion of this mass x and the angle theta? So it is given that there is no slipping between the pulley and the rope. So that means that uh, by whatever rate that the mass will descend or go up, so uh, the pulley has to rotate by an angle such in such a way that it will match the angle, the amount of rope that is unwound or wound back onto the pulley uh, on its circumference.
Arc equal to the distance displaced moved by the weight.
Right. So basically, uh, so the thing is basically that so the change in the displacement delta x, it will be, so let us say when there is a small change in the displacement, let us say delta x, and the pulley rotates by some small angle delta theta. So the relation between this delta x and theta is basically delta x is equal to r into delta theta, or other way on, or alternatively we can just write it as simply as x is equal to r theta. So if x is the displacement of the mass from its equilibrium position, so this is the first important thing that we should first realize, that x is equal to r theta. Then the next step is to draw the free body diagram of each component. So we just defined like there is some coordinate system, so with respect to which like we can say that the coordinate system is maybe something like this x y. So so let us say this is the displacement x is with respect to its equilibrium position of the mass. So in equilibrium there will be some deflection of the spring, etc. So that is taken care of. So when we talk about displacement from the equilibrium position, so then uh, the displacement of the spring, or basically the extension of the spring because of the weight of the mass small m, is taken care of when we say that uh, the so the displacement x is with respect to its equilibrium position. Or if we do not want to say that it is define it with respect to equilibrium position, we can choose a coordinate system at the center of this discs, let us say, and then we define the position of this mass as x, let us say. Then uh, so then the if the if the equilibrium, at equilibrium position, let us say this it is at x st, or let us say with equilibrium position is, let us say, x eq, and let us say at some general time instant it is at some position x. So it has moved by an amount x minus x eq. So or if we say this is x1, so the x1 minus x eq, it is basically this x which I was talking about. So it is with respect to the equilibrium position. So this is the displacement. So now we will first draw the free body diagram of each component. So let us say there is some tension T acting on this mass small m, and then there will be weight mg acting on the mass, and then let us draw the free body diagram of the pulley. So let us call this tension as T1. So this is tension T1 and let us say this is tension T2, which is exerted by the spring. So this has moment of inertia J. The pulley is not massless. It has some moment of inertia, and the free body diagram of the spring. So let us say the spring is massless. So the tension between the two ends will be same, T2 itself. So then we now derive the equation of motion for each of these components. So like we assume the coordinate system like this. So x, y. So then the downward direction is positive. So then we can write mg minus t1 is mx double dot as the equation of motion. So we'll apply the Newton's second law to this mass small m. So we can write down the net force acting on this mass is mg minus t1, which is equal to mx double dot. And for the disk, we will take the moment about its center of the disk. So what will be the net moment about the center of the disk? Let us say we assume that anticlockwise direction as positive. So then we can write T2. So the radius of this is small r. So T2 into radius minus T1 into radius. So the moment exerted by T2 will be anticlockwise, whereas the moment by T1 tension will be clockwise. So it will be minus T1R. So which is J theta double dot. And we know that theta is equal to x by r, or x is equal to r theta, whichever way we want. So we can eliminate either x or theta by using this relation. So we can either write it as j theta double dot as j into x double dot by r. And similarly for the spring force, so T2, it can be written as k into deflection of the spring. So the deflection of the spring is related to the displacement x. So because we are saying that x is with respect to the if x is with respect to the equilibrium position, then we actually do not need to consider this force mg, because in that case we are already accounting for uh, the equilibrium with respect to equilibrium position, so we don't need to consider the force mg. But let us say if we are talking about the absolute position, so we coordinate, let us say x1. So then how do we write the deflection of the spring? So it will be k into the let us say the position of the mass is given by x1. So it will be basically x1 minus x static, so which is basically the displacement from the uh, equilibrium position. So that is the additional elongation of that spring. So let us say basically this point, let us say it moves by some amount x2. So this point also moves by the same amount x2. And now we are saying that this position of uh, this thing. So this will be basically the displacement of the spring, and the net spring forces will be like this basically. So now we can say that K into X equilibrium will be related to the force mg. Or if we want to write about the equation of motion about the equilibrium position, so then we can just remove the force mg and just write this way, and then which is equal, and this we can also write as, so to keep things simple we can just write it in terms of x instead of x1. So what we will get now as the equation of motion, so we know that T1 is minus mx double dot, and in this we can substitute it in this equation. So T2 is kx, so basically kx into r plus, so it will be basically minus T1 into r, so minus T1 into r will be mr x double dot, which is equal to j into x double dot by r. So we can write it as j into x double dot is equal to, so here if the now here we have to follow a sign convention now here. uh, so if we say consider that angle theta, if we are considering that that our displacement downward it is positive, then that will cause a clockwise rotation. So a downward displacement will cause a clockwise rotation of the mass. So it's actually, uh, but we are saying that anti-clockwise rotation is positive, let us say if we follow that convention, so then this relation will actually be theta is equal to minus x by r, because a positive down, like if downward displacement is positive, so that downward displacement will cause a clockwise rotation, which is actually negative, because we are considering anti-clockwise rotation as positive. So in this equation, it will actually become minus jx double dot by r. So it will be basically right hand side will be like this, minus jx double dot by r. So now if we multiply on both sides by r, so we will get mr square x double dot plus kx. So if we take the j x double dot term on the right hand side, so we will get basically mr square plus j into x double dot plus kx is equal to 0. So we can write it as x double dot plus k upon mr square plus j into x is equal to 0. So therefore, if we compare it with this form, x double dot plus omega n square into x, where n is the natural frequency omega n, so then we can write down that omega n is root of k by mr square plus j. So this is how we can solve this problem. So any questions on this?
Sir, can you highlight the equations you used to equate?
Yeah, so first is basically uh, to find out this relation. So as I mentioned that there is, because of the sign convention, this will become x is equal to minus r theta. So we are assuming that anti-clockwise rotation is positive and downward displacement is positive. So that causes this relation to become x is equal to minus r theta first of all. Then in the free body diagram, we show the tension and uh, the other forces and apply Newton's second law. So these are the set of equations for these components. Uh, so this is for this mass small m. This equation is for the disk. So we take the moment about the center of the disk. So we get a relation between the two tension forces TO, T2 and T1 in terms of the motion of like basically the rotating motion of the disk, and then finally we get the tension value in terms of the spring force, so T2. So the spring force is again related to the displacement of the mass small m, so which is k into x. So finally we got the value of tension T2 in terms of the motion x, then the value of the tension T1 in terms of the motion of the small mass x, and then we on the right hand side we have the term j theta double dot, so which we also again know in terms of x, and so finally we combine all these equations to get this equation of motion. So this is the equation of motion, and then from that we calculate the natural frequency.
Yes, sir.
Okay. So we can similarly look at another problem. We may not be actually go into the full detail of this problem because we have only like about 10 minutes left. But we can see the how to approach this problem. So here this is also a question from one of the GATE papers. So probably something around 2017 or so. I don't remember exactly, but so this question it says that so this there is a uniform rigid bar which is has a length L and mass capital M, and it is hinged at some point O, and the length of it is at a length L by 3, and there is a spring at both the ends, and there is a small part mass M, which is capital M by 4, and it is fixed at one end of the bar. So we have to find out for small rotations of the bar about O what is the natural frequency of the system. So I'll just quickly go through how to approach this problem. So if we draw the free body diagram of this bar, then so let us say this is the center of mass of the bar, and there will be the weight capital Mg acting on the center of mass, and it's also given that there is a small mass small mg at this end. So and this is let us say the hinge. So because of the hinge, let us say there is some force Fy and some force Fx acting on at this hinge point, let us say O, and will call the center of mass as G, and let's call this point as A and this as B. So at points A and B, so there will be a spring force. So now because this uh, rod has tilted by some angle theta, the spring on this left hand side will get compressed. So let us say we write it as k into delta 1. So where delta 1 is the deflection of this end A, or let us call it as delta A itself. And then there will be another spring force here which will be tensile because this spring will get extended on the right hand side, and we'll call it as k delta B. So the most important thing now is that because the deflections are small, we can write that delta A is nearly equal to OA into theta, and delta B we can write it as OB into theta. So which is so OA is basically L by 3, and delta B is So it will be 2L by 3 into theta. Okay. So now to solve this problem, what we will have to do is to take the uh, moment about point O, let us say, of all the moment of all the forces about O, and that will be moment of inertia of the bar and the mass, whatever that mass, small mass together. So let us say Jo is the moment of inertia of the bar about point O plus the moment of that small particle mass about that point O will be basically m into 2L by 3 whole square, because it is located at a distance 2L by 3 from O, this whole thing into theta double dot, and the left hand side we can calculate it in terms of the forces. So assuming again similarly that anticlockwise is moments are positive, so we will get basically, so the distance OG will be L by 2 minus L by 3, which is L by 6. So Jo will be the moment of inertia of the bar about its center of mass Jg plus capital M into Og whole square, which is M. So that will be the value of Jo, and the left hand side we can find it out as, see, the moment due to the weight, so it will be basically minus mg into the length og, so which is L by 6, and because of the small moment, weight of moment of the small mass is weight, and the spring force k delta b is also cause of clockwise moment, and so it is k delta b, which is, and it is at a distance of 2L by 3 again, and the moment because of the force k delta A will also again be clockwise, and it will be at a distance of L by 3. So this is basically summation of moment about O. So now we know that delta, we know the values of delta B in terms of theta. Uh, so minus k into 2L by 3 theta into 2L by 3 minus k into L by 3 into theta into again L by 3. So so it is basically J equivalent into theta double dot. So we can simplify this equation, differential equation further, and then we can uh, get the simplified differential equation. So from that we can find out the natural frequency of this system. So I suggest that you can actually try simplifying this equation further. So we can discuss it in the next session. So I think we can conclude this session for today at this point. So any questions till now?
No, sir.
Okay, sure. So I think we'll stop here for today. I'll share the slides and with you, so you can actually try out this example. You can have a look at the slides and we can discuss in the next session if you have any doubts or any questions, and we can uh, discuss the answers in the next class. So thanks for joining.
Thank you, sir.
Yeah, thank you.